So the first thing before we start analyzing and designing amplifiers, let's, in this particular lecture, look at some of the important amplifier characteristics. Now, there are several, and I'll only cover a few of them, which, we'll address in this particular course here. And these are some of the things that we keep in mind here. Some questions to keep at the back of your mind. Can an amplifier with a rating of 100 voltage gain provide less gain than an amplifier with a rating of 10? All right, it's a little bit ambiguous, but you'll see what it means. Why does an amplifier's performance degrade at higher output power? How small a signal can an amplifier amplify? Right, what are the limits? So this is a limit on the lower end. How small a signal can an amplifier work with, and this is a limit on an amplifier at the upper end. If you make a signal too strong, or if you want to have too much output power, then again there's a problem here. All right, so first of all, before we start looking at amplifiers, there are 4 classes of amplifiers that one can have here. This is a simple picture of an amplifier that you see. We have an input here. Input is written in a general form Xn, and output here X0. Every amplifier will have power supplies here. And the way an amplifier amplifies is, it basically takes the power from the power supply and delivers it to the load here. The power that comes from the input is very small, obviously. So if we have said earlier, you can call a device as an amplifier only if there's a power gain. Power gain meaning the power here, output power divided by input power, is larger than 1. Now, if it is larger than 1, of course, there has to be conservation of energy. So where does the extra power come from? It comes from the supply here. So what happens is power is taken from the supply here and delivered to the load. Okay. Now the input here, as you can see, can be in general, if it's an electrical signal, can be a voltage or a current. The signal could be a voltage or a current. The output also could be a voltage and a current. Okay. Then there are 4 possibilities of looking at an amplifier. If input is a voltage, output is a voltage, we call it a voltage amplifier. Input is a voltage, output is a current, we call it transconductance. Current will obviously be called a current amplifier, and input and output are transresistance here. Now you must be wondering, if I apply an input, obviously I'm going to have both of them. I'll have voltage as well as current. Similarly, when I look at the output, I'm going to have both of them. I'll have current as well as a voltage as well. Right? So the point that is being illustrated here is that the amplifier is designed in order to maximize this quantity, voltage gain. Okay? Then we call it a voltage amplifier. So our interest is in V0 divided by Vin. So it's designed like that. Of course, at an input and output in general, we'll have both voltages and currents. Okay? Similarly, the amplifier is designed keeping in mind that I'm interested in current as an output current here, and voltage as an input here. So it's designed with that in mind. And therefore, the ratio of current divided by voltage, output current divided by input voltage, so we will call it a transconductance amplifier. So the quantity that I'm interested in is transconductance. I0 divided by Vin is conductance, and because they are associated with 2 different ports, we call it a transconductance here. So now, current and current, obviously we call it a current amplifier, and then transresistance amplifier. Now there are applications where one's interest is in current amplifier. There are applications where one's interest is in transresistance, and similarly transconductance. In this particular course, we'll address primarily voltage amplifiers, where our input is a voltage, where the signal is a voltage, and output also we are interested in voltage. Okay, so we are interested in amplifying the voltage from a small value here to a large value here. So voltage amplifier is what we are interested in. But keep at the back of your mind that aside from voltage amplifiers, we have transconductance amplifiers, current amplifiers, transresistance amplifiers as well. And they will be designed in a different way. Okay, keep it, because the quantities of interest are different. So ideal voltage amplifier, well, the schematic denotes that what I have is a signal here, a voltage signal here, and at the output I have another voltage signal here. The point to remember is, to look at it, is that to call something an ideal amplifier, the output should be a faithful reproduction of the input here. Whatever is the shape, the same shape should appear over here. The only thing that should differ is the magnitude. I should have a higher magnitude here as compared to the magnitude here. The shape has to be exactly the same. If it's a sinusoid, I want a sinusoid here. If it's a triangular wave, I want a triangular wave here. Only the amplitudes should differ. Okay? And therefore, an ideal amplifier I can describe by this relationship. V0 is AV times Vin. So V0 is nothing but Vin, but multiplied by some constant factor. AV is a constant. It's a constant factor here. So that's what we are looking for in the characteristics of an ideal voltage amplifier. AV, remember, has to be a constant. Okay? Note that if AV does become a function of Vin, then what happens is V0, this relationship becomes nonlinear, and therefore you can still call it an amplifier, but it's not a good amplifier because the output will be distorted. The output will be distorted here. The other, whenever we draw these signals, what happens is many times we characterize the amplifier by putting in a sinusoid. The output is also a sinusoid. Don't get it embedded that amplifiers, the purpose of an amplifier is to amplify a sinusoid. No. In fact, sinusoid carries no information. A simple sinusoid carries no information. It's just for the purpose of characterizing an amplifier that we often, apply a sinusoid at the input and, look at how the amplifier responds. And we also keep in mind that any signal can be broken down into a sum of sinusoids here. Okay? So for that reason, most of the time we characterize it with a sinusoid. So AV has to be a constant in an ideal voltage amplifier. Now, of course, practical amplifiers are different from ideal, and they differ in several ways. This is more realistic. So this is what you want. AV has to be a constant, and this is what is more realistic. The voltage gain that you have depends on several factors. The voltage gain, which was supposed to be a constant, depends on frequency, depends on load resistance, what value of load resistance you connect, depends on what value of source resistance you connect here, okay? What value of, what supply voltage you've applied, what is the temperature, depends on, this relationship between V0 and Vin is often nonlinear, which means that AV is also a function of Vin. So you have all these non-idealities. Plus, in addition, you get a bonus here. When you don't apply anything, you still get something out, which is the noise here. Okay, so noise is also present. So these are all the sources of non-idealities. Because if you compare this relationship with this one, this is what you want. AV is constant. And what you end up with is all these dependencies. So let me describe some of these dependencies in this particular lecture here. All right, so the first thing that I'm going to look at now, here, the way gain has been designed is V0 by Vs is what we have defined the gain as. Okay, so let's start by looking at some of the non-idealities here. Okay, so this is a okay, so this is an amplifier. All right, so an amplifier here, and what we we have a signal here. Every signal will have in general a resistance associated with it. Voltage signal will have some internal resistance here, Rs. This is my amplifier, and we have connected a load here. And what we are looking at right now, so note that there are different ways in which one can define a gain. I can define a gain as V0 by Vin. I could also define a gain as V0 by Vs here. So right now, what I'm looking at is V0 by Vin. So when I define V0 by Vin, what will happen is the gain will not depend on Rs, because Rs is prior to Vin. Okay, if I were to define V0 by Vs, then the overall gain will obviously depend on Rs. So my purpose right now is to concentrate on the effects of RL. So that's why I've defined it as V0 by Vin here. So we are looking at this particular gain. And so along the y-axis, we have this particular gain. And then what I'm doing is I'm changing RL. RL is here along the x-axis. So I'm going from RL equal to very large value, let's say infinity, which means the quantity that I will have, infinity means very large value of RL. The quantity that I will have is what we call as open circuit gain. Very large load resistance or an open circuit here. So the gain V0 versus Vin, we will call it as a open circuit gain here. So we call it AV0, O referring to open circuit. Okay, so it starts off with a gain here. Now, as I steadily reduce my RL, what happens is gain remains constant up to a while, and then starts dropping. Starts dropping and keeps on dropping. A stage is reached where, for example, the gain has dropped to half its open circuit value here. And it will drop at a particular value of load resistance, RL, and that value of load resistance is what we call as output resistance. Why we call it output resistance will become clear in a minute. So this is the behavior that we see here. An ideal amplifier should have a totally flat characteristics. No matter what load resistance I connect here, it should be constant. That's what an ideal amplifier is. All practical amplifiers will have the gain that is dropping with RL here. Now, at what point it starts dropping and at what point it becomes half depends on how the amplifier has been designed. And what characterizes this particular phenomena is this quantity called R0. R0 describes this particular behavior here, output resistance. Okay? All right. Now, the way we conceptualize the effects of output resistance is, now it's coming about because of RL, because of changes in RL that we see here. So if I look at my amplifier from the output side, I can write, now remember, when we are looking at an amplifier, amplifier is a linear, we want it to be a linear device. Linear means whatever is inside an amplifier, I can make a Thevenin's equivalent of it. Okay? Whatever resistance is, whatever current source is, whatever it has inside it, I can always write a Thevenin's equivalent of it. So when I look at an amplifier from the output, I can describe it by these two. You can see here, this is like a Thevenin's voltage, and this is like a Thevenin's resistance here. Okay, so when, in the context of amplifiers, when I look at it from the output port, I describe it by a resistance, Thevenin's resistance, if you would like. We call it a output resistance R0. And the source here, the voltage source here, what is the source of the voltage here? If I look at it, eventually it is the input voltage here, which is getting amplified and appearing at the output here. So we call this as AV0 times VA. Okay, and so that's what an amplifier looks like from the output side here. Two quantities, AV0 times Vin, note Vin here, and R0 here. Now we can connect an external load resistor RL here, and then one can easily write down that the voltage gain V0 by Vin will be equal to AV0, or V0 will be equal to AV0 Vin, RL by R0 plus RL here. So you can see there's a drop taking place across this one, and therefore it tells us, you know, if I take this V0 by Vin and I plot it, I will get this particular graph. Okay, so you explain this particular characteristics of gain dropping with respect to RL through this particular model here. That when you look at an amplifier from the output side, you do see an R0 output resistance and you see a AV0 times Vin here. And one can see why we are calling it AV0. If I open RL, make it infinite, then of course the voltage simply becomes V0 equal to AV0 times Vin, and therefore V0 divided by Vin will give us AV0. Okay, so it makes sense to call this quantity AV0 here. Okay. All right. Now the other is, so you can see here that when I make R0 or when I make RL equal to R0, the overall voltage gain falls to half here. So one of the definitions or one of the ways of defining output resistance is the value of load resistance that I need to connect such that the voltage drops to half its value as compared to its open circuit value. Okay, or the voltage gain drops to half its value here. At what point does my output resistance begin to matter? This is of course output resistance has become a serious issue here. But note that the voltage gain begins to start falling maybe when my load resistance is about 10 R0. Right? The voltage gain, if I make RL equal to 10 R0 here, the voltage gain has already become something like 0.9. It has fallen by 10%. So when does my output resistance begin to matter? As a rule of thumb, we can say when my load resistance become less than or equal to 10 times R0. 10 times R0. Because as I start decreasing the load resistance beyond 10 times R0, of course the load then we are on this particular curve. Okay? So this could be taken as a sort of a limit here. That if you keep your load resistance larger than 10 R0, then you're okay. You're getting the maximum gain that your amplifier is capable of. If RL is less than this value here, then of course your gain is falling because of R0 effect. All right. Now R0 is not the only thing about a amplifier when you look at it from the output side here. All of you have done your, you've analyzed op-amp circuits, you've made op-amp circuits in the lab as well. Now, what I'm trying to illustrate is a point here that besides output resistance, there's something else which is important, which is the maximum current driving capability from the output side. Every circuit has a limit on how much current it can drive, how much current it can drive into a load, or how much current it can sink, how much current it can sink, right? So remember, if the voltage is positive, it's driving a current into the load. If the voltage is negative, what is happening is the current is going from here into this here. So it's acting as a sink. So every circuit will have a limit on how large a current it can source and how large a current it can sink. And that limit is also important. And many times, if you don't take care of this particular point, you can't understand why the circuit is behaving in a particular manner. And this one will illustrate. Okay. So look at this particular circuit here. Simple inverting amplifier. R1, R2. So we expect a gain of this particular amplifier is minus R2 by R1, V in. And so if I apply minus 1 volt, I expect 10 volt here. I expect 10 volt here. Now, normally when you've analyzed your op-amp circuit, you had not connected an RL. Okay, normally we don't. I mean, many times when we analyze, we don't connect it here. So anyway, for a moment, you forget about RL. Okay, you forget about RL. I expect V0 to be 10 volt. Now, we know that this whole thing is an amplifier, and therefore it will have an output resistance. Okay, when I look at from here, it will have an output resistance. And the output resistance of your 741 op-amp is very small to begin with. And you can see here that we have put a negative feedback also. And later on, you may learn that when you put negative feedback in this manner, you further lower the output resistance here. So just for the sake of argument, let me say that the output resistance for this one is less than 1 ohm. Okay? Because as I said, the output resistance initially is large here, small, and further negative feedback will further lower it. Output resistance, let's say, is less than 1 ohm. Now, how much load resistance can I connect here and still get 10 volt? What did we just study here? We studied that I can connect a load resistor as low as 10 times R0 and still my output voltage should, remain the same, right? So if I say my R0, let's say, is 1 ohm for the sake of argument, how large an RL I can connect? At least 10 ohms. So till 10 ohms, RL of 10 ohms, my output should not vary. I should keep on getting 10 volt. So whether I connect 10 ohms here, whether I connect 100 ohms here, whether I connect 1 kilo ohm, 10 kilo ohm, I should get the same value of 10 volt. All right. So go ahead and make this particular circuit in the lab and see what happens here. So this is what we expect, right? It should remain 10 volt till I reach a value of RL equal to 10 R0. Okay. If you build it in the lab, this particular circuit, or if you simulate it, this is what you find. V0 starts dropping not at 10 R0, which is 10 ohms, starts dropping at 400 ohms. Now, that violates our concept of what we just learned. We said that you can put RL as small as 10 R0. This is 10 ohms. So why is it dropping at 400 ohms? Okay, if output resistance is only 1 ohm and I connect 400 ohms, why is it causing my output voltage to drop? Now, this concept you can't just simply explain only on the basis of R0. That's what I'm trying to tell you. There's something else that is important. And that something else is the current driving capability. Because this op-amp that you see here, as I said, every circuit has a limit on how much current it can drive and sink. Now, let me explain why this is happening here. This op-amp that you see here, 741 op-amp, has a maximum current driving capability of around 25 milliamperes. Internally, it cannot, its limit is it cannot give you more than that. Okay. So now we see here, if this is 25 milliamperes here, and I connect 400 ohms. Okay. Now when I connect 400 ohms, what does this current have to do? This current, 25 milliamperes, has to supply a current here that goes here. And remember, this is like a virtual ground, and this voltage is positive 10, and this is 0. So a current has to flow here, and another current has to flow down. So when I'm at, you see, we expected how much here? 10 volt. Why am I not getting 10 volt here? Well, if you look at this 25 milliamperes, I'm getting only 9.6 because 9.6 divided by 400 gives me 24 milliamperes here, and 9.6 into 10K here gives me another 0.96. So the two add up to almost 25 milliamperes. So I get 9.6 here only. I don't get 10. Similarly, for example, suppose I put here 100 ohms. 100 ohms here. 100 ohms is much larger than my 10 ohms here. Output resistance of 1 ohm, right? If I put 100 ohms, how much value do you think you'll get here? How much value do you think you'll get here? 100. Well, maybe I have here. 100. Well, I don't have the answer. So 25 milliamperes, how much will you get here? Let's say assume a value of V0. Okay, assume a value of V0. For that value of V0, you need a current here, which is V0 by 100. And you need a current here, which is V0 by 10K. That current of 10K is obviously much smaller than 100. So how much will you get? V0 by 100 equal to 25 milliamperes. So V0 is equal to 25 milliamperes into 100. And how much? 2.5. All that you will get is 2.5 volt at the output here. You will not get 10 volt here. And my resistance is still much larger than my output resistance of 1 ohm. So where is all this phenomena coming from? Because my op-amp has a limit on how much current it can supply. 25 milliamperes here. Similarly, it has a limit on how much current can flow in the opposite direction here in terms of sinking. It can sink also current of comparable magnitude here. So besides output resistance, another quantity to keep in mind is your output current driving capability. And these become very important as the signal becomes larger and the output resistance becomes, the load resistance becomes smaller here. Okay. All right. So that's from the output side. Let's look at it from the input side here. Input resistance. Well, now we know what is the effect of RL. So for a moment, I've removed the effect of RL here. Okay. And I'm now interested in RS here. And we are defining the voltage gain as V0 by Vs. What effect does RS have on my amplifier here? V0 by Vs is the gain. And then I plot it out. When RS is 0, here, the entire signal goes here and the gain is AV0 here, open circuit gain. And then as I keep on increasing RS, for a while the output remains constant or the gain remains constant. And after a while it starts falling. It starts falling here, and the place where the gain becomes half is the place which we call as at that point, the value of RS is equal to the input resistance here. Okay. And so we note that the gain, overall gain, V0 by Vs, the signal, if this Vs is the signal and V0 is output here, does depend on the source resistance that you connect. And we explain that phenomena on the basis of Rn. And the way we do it is, we say amplifier, when you look at it from the input side, has a resistance here, Rn. Okay, and this is the value that we put here, input resistance here. And now one can easily see why the gain is falling as a function of RS here. If I calculate V0 by Vs, now from the output side, I've put all of these here. So V0 by Vs, which we call as AVS here, will be equal to AV0. This is the first part here, Rn by Rs plus Rn here, because what gets amplified is what gets appeared across the amplifier here. So out of this Vs, there's a voltage divider, and so there's a loss here. The loss that you see here, because only a part of the input voltage gets applied here. And this we've already studied, RL by R0 plus RL. And you can obviously see when I make Rs equal to Rn, then my gain falls to half its value here. Okay, so that's the other thing to keep in mind. Every amplifier will have an input resistance. It may be large, it may be small. All right, so this brings us to an interesting question here. Say you're given two amplifiers, right? And an amplifier with a gain of 10 to the power 2, 100. Which gain? Open circuit gain. Because the actual gain now will depend on the circuit. What value of load you connect, what value of source you connect, and all that. So an amplifier has a gain of 100, input resistance of 1K, output resistance of 1K. That's one amplifier, let's say, you're given. Another amplifier has an open circuit gain of 10, input resistance of 100K, output resistance of 1K. Now you are out to shop for an amplifier. Which one will you prefer? Let's say both of them cost you the same. Which one will you prefer? Now, what I want you to do is create situations on your own, create situations where you can show that there are situations where I would prefer this one, and there are situations where I would prefer this one. It all depends on what your application is, where you're going to use this particular amplifier. So I want you to create those situations, and I think it's a part of the homework assignment, next one, where you have to create those to show that in that case I will prefer amplifier 1. In some other case I'll prefer amplifier 2. And I'm sure you can see what the differences are. You can obviously see an R in here. You know, if you have an amplifier, if you have a source which has a very large resistance, then maybe this will become preferable. Okay? Because remember, as an application, you're not just interested in V0 by Vin. What your interest is in V0 by Vs, the actual signal voltage here. Okay? The other one is, look at this one. AV0 equal to 1, Rin equal to 10K, R0 equal to 10 ohms. Is that a useful entity? It has a voltage gain of 1, right? Is it a useful entity? It has a gain of 1. Now, gain of 1 means what? We are saying V0 equal to Vn. Is it not same as a wire? A simple wire is also V0 equal to Vn. Right? So why do I use an amplifier? Just connect a wire. Wire will give me V0 equal to Vn. Alright? So is that a useful entity at all or not? Think about it. See how you can, if you're given something like this, you can use it to your advantage. Okay? Alright, so I'll leave you with those questions. Let's come back now. We have seen input resistance and output resistance. And we have also looked at output current driving capability. Let's next look at the time response, or another way of saying it is a frequency response. These two are complementary in some sense. So every amplifier will have a frequency response. Here I've plotted the voltage gain, 20 log 10 AV. Let's say this is AV0, open circuit gain, AV0 as a function of frequency. And in general, what you find is the gain in general, that the gain falls at very low frequencies, remains constant, and there's a range here, which we call as the mid-frequency range, and then the gain falls at higher frequencies. Okay? This part is almost always there. The gain will always fall at higher frequencies of all amplifiers. This part may or may not be there. Okay? Depending on how the amplifier is constructed, this may not be there. So now, this is the useful range of an amplifier here. Now, remember, if I have a signal here, let's say it's a music or a speech or whatever. Now, you don't want different signals of different frequency to be amplified in different manner. Then you're distorting, in some sense, the signal, right? So, for example, if a lower frequency signal, you have a certain content in your signal, which is lower frequency, and if that doesn't get amplified, and then there are certain higher frequency signals that also doesn't get amplified, then obviously the output will not be a faithful reproduction of the input. So the useful range of an amplifier is this one here, the constant range here, where the amplifier's response is frequency independent here. Of course, there are places where you may be deliberately wanting this to happen. That's a different issue. You may want some lower frequency signals to be attenuated. If that's an issue, that's separate. But in general, if you want output to be a faithful reproduction of input here, then you want to work in this range here. And this range is defined by two limits. There's an upper frequency limit here, and there's a lower frequency limit here. So we have to be aware of this lower cutoff frequency, lower 3 dB cutoff frequency, and an upper 3 dB cutoff frequency here. So an amplifier works in this particular range from FL to FH here. Okay, so that's an important parameter of a amplifier that one needs to be aware of. As I said, some amplifiers may not have this particular part here, which you see here. They will amplify even a DC signal here. And we call it a DC amplifier for that reason, that even a zero frequency or a DC signal can be amplified. Doesn't mean that it cannot amplify a 1 kilohertz or a 10 kilohertz. When we call something a DC amplifier, means it's also capable of amplifying a DC signal here. Alright, so it doesn't have a lower cutoff frequency. It goes right from zero frequency and then has only a upper cutoff frequency. Okay, and in relation to this frequency response, sometimes we also quote a quantity called unity gain frequency, is the frequency at which my gain becomes equal to 0 dB, which means gain becomes equal to 1. So sometimes, you will hear manufacturers quoting, let's say, or in terms of specifications, FH and FL may be given. Sometimes in addition to that, you may be given a quantity called FT, where the gain becomes equal to 1 or 0 dB here. Now, transient response is also sometimes important, because these frequency response that you see here is a small signal frequency response. where my input voltages are small in magnitude. In transient response that we apply a large input voltage here. The input voltage is not so small. And there are applications where this is of interest. So if I, for example, if I take an amplifier and let's say applied a input voltage here, a square wave that you see here, a pulse, what happens is the output takes some time to respond. And then the output again takes some time to respond on this side here. So what you see here is I have a rise time and I have a fall time. Okay, so amplifiers can be characterized by how much is the rise time and how much is the fall time. Okay, so here we have applied an abrupt input here, and so rise time and fall time are important quantities. Sometimes when you apply an input like this, what you may see is this kind of a response. The output, here it shows output, you know, monotonically rises and settles down to its value here. And sometimes the amplifier's response may be like this here. Okay, you see overshoots and undershoots and gradually it settles down. So what becomes important here is that how much overshoot do I get here? How much overshoot do I get here? How long does it take after it reaches this value? How long does it take to settle down? So those become important parameters here. What is the overshoot? What is the settling time? Another interesting thing is a slew rate. These are all quantities that describe the transient response. So what I'm illustrating here is a op-amp who's connected in the form of a buffer, where, as you can note here, you expect V0 to be equal to V in here. Now, if you apply a square wave, let's say, and if you keep on increasing the frequency, what you may find is a response like this here. This is a square wave here, and the op-amp goes like this here. Linearly rises, and then reaches a steady state value, and then linearly falls here. Okay, and this phenomena, we say that the op-amp is slewing to its final value here, and the rate at which it rises is what we call as a slew rate here. dV0 by dt is the slew rate of the amplifier here. So these, slew rate, overshoots and settling time, rise time and fall time, these are all parameters that describe the transient response of your amplifier here. And for example, the frequency response doesn't give us that particular picture. I may know the unity gain frequency, I may know the lower cutoff and upper cutoff, but that will not tell me how will an amplifier respond under this situation. What will be its slew rate? Okay, so these are separate parameters that I need in order to predict how my circuit will work in certain situations. So slew rate is another important parameter. Okay, this is a very important parameter called distortion. Now, what this is illustrating is that all amplifiers that I build, I will build it using a transistor, whether bipolar or a MOS. And these are all nonlinear devices. You can see here. These are all nonlinear devices, meaning that if I look at my base current versus base emitter voltage, we know it's a diode, it's an exponential characteristic. It's a nonlinear device. And in an amplifier, what are we looking for? We are looking for a linear relationship. We are wanting V0 to be linearly related to Vin. Okay. Now, you can see how is the voltage gain getting developed. If I look at this one here, Vin, if you note here, what Vin does is, it causes a change in IB. Right? Vin is the source of IB. Alright. Now, what is the relationship between IB and Vin then? Nonlinear. Nonlinear relationship. So, IB is related to Vin through a nonlinear relationship. What is the relationship between IB and IC? Linear. IC equal to beta times IB. So that's not a problem. But IC, how will it be related to Vn? Nonlinear. And then what develops a voltage here? This voltage is nothing but VCC minus ICRC here. So what will be the relationship between V0 and Vn in general? Nonlinear. So amplifiers are inherently nonlinear. The only way you make them linear is by keeping the voltage very small. If you keep it very small, then you can say, well, within that range, the amplifier is linear. So distortion, and anytime a device or a characteristic is nonlinear, I will get distortion. So let me explain what happens here. So here is an amplifier, let's say V in V0 here. And suppose I apply an input voltage here, which is A0 sine omega t. Now, if the amplifier were totally linear amplifier, then what will I get? V0 will be equal to V in multiplied by whatever is the gain. Let's say if the gain is 100, I will get 100 times A0 sine omega t. but my amplifier is nonlinear, which means that in addition to this fundamental frequency, I get what? I get second harmonic, third harmonic, fourth harmonic, all of that comes in. Why? Because this is nonlinear. So in addition to fundamental frequency here, I see all these harmonics here. And how do I characterize distortion? Well, I call a quantity called second harmonic distortion. HD refers to harmonic distortion and 2 refers to second harmonic. Why? Because I'm looking at the amplitude of the second harmonic, which is B2, relative to the amplitude of the first harmonic in which I'm interested in. Because my signal is omega, so I'm interested in this part. But I'm getting in addition this particular part here. So B2 by B1 is a measure of second harmonic distortion. Ideally, I want HD2 to be 0. Similarly, HD3, third harmonic distortion is B3 here. Third harmonic divided by B1 into 100 here. So like that, we can calculate HD2, HD3, HD4 and so on and so forth. One can also calculate total harmonic distortion, which is B2 square plus B3 square and all of that added up in RMS fashion here divided by B1. So that's called the total harmonic distortion, and these are individual harmonic distortion. So that's how we measure harmonic distortion. Okay, so when we take an amplifier, the manufacturer may quote that it has a total harmonic distortion of so much in terms of percentage, 5%, 2%, 1%, and so on and so forth. Okay, so that's the meaning of harmonic distortion. Yes. Look at this example. The next one. Suppose I have a nonlinearity V0 versus Vin, which is of this kind. I have V0 is K Vin plus K by 10 Vin square. So this is what I am interested in, and this is a very simple nonlinearity that I get here. So again, if I substitute Vin equal to A0 sine omega t here, what I will end up getting, you can easily work out K A0 square by 20, K A0 sine omega t minus K A0 square by 2, 20 cos 2 omega t. Because we were getting sine square omega t, so we convert it into cos 2 omega t here. So in addition to a sine term here, fundamental, I get a 2 omega here. And so I only get a second harmonic distortion here. So my total harmonic distortion is equal to second harmonic distortion, which is equal to K A naught square by 20 divided by K A naught, and that's equal to 5 times A naught here. So that's my harmonic distortion. This one doesn't matter for me because I can easily filter it out. DC is a DC part here. So this is what bothers me. The fact that I've put in a fundamental and I get 2 omega as well. Now, apart from that, so apart from let's see, important point to notice here is the following. Distortion that you see here depends on A naught. And A naught is what? The amplitude of the input here. Now, this I'm showing only through a specific example, but that is in general true, that as you increase the amplitude, the distortion increases in your circuit here. Okay, input amplitude. Now, remember, if you want, if you want to hear, let's say, something which is very loud on a speaker, what will you do? You want to drive more power into the speaker. More power into the speaker means more output amplitude. More output amplitude basically means more input amplitude here. And more input amplitude means more distortion here. Okay, so that's why when you drive things at very high power, what you are also doing is the input amplitude is rising in correspondence to that, and that's one reason why you may see distortion increasing with the signal here. And in general, all that it is illustrating also is, in general, I have nonlinearity in my device. All my transistors are nonlinear, and therefore I will get distortion. And distortion then becomes very important. It also tells you that when you specify distortion, you always have to specify distortion at a particular level. Here it is being written as at a particular value of input level. I can also specify harmonic distortion at a particular value of output level here. There's no meaning to saying I have a distortion of 5%. You always have to say 5% at what? 5% at an output power of so much, or 5% at an input signal magnitude of so much. You always have to specify like that. Simply saying 5% or 2% is not enough. This is illustrating another source of distortion here. In the previous case, I was denoting distortion due to the previous example, the fact that my input is sort of nonlinear. Now, this shows you that when I look at my output versus input graph, I will always get something of this kind. That as I keep on increasing my input, my output follows and the slope gives me the gain. But if I keep on increasing, there's a limit to how large my output voltage will go. All of you know that if I take a 741 op amp, I bias it at plus minus 12 volt, then my amplitude cannot exceed 12 volt here, which means I start getting a saturation here. And then I will start getting a saturation here. Now, obviously, if I have a situation like this, let's say the saturation voltage is a 5 and minus 5. If I apply a 0.8 volt input, 0.8 volt input here, it's expecting it to go larger because the gain, let's say, is greater than 10. So I expect output to go beyond 8 and beyond minus 8 here. All that it will go is 5 here and a minus 5 here. So obviously when I get clipping here and I get a clipping here, output is distorted and that will show up as a harmonic distortion. I will get second harmonic, third harmonic, fourth harmonic and all that. So I don't have a pure sinusoid, I'll have a harmonic distortion here. So that's coming about because of limitations here. That there's a limit on how large the output voltage can be and how small the output voltage can be. Okay, so the saturation here and saturation here. So that brings us to the concept of rail-to-rail output voltage swing. Now, if you go and read the data sheets of amplifiers, you will find manufacturers prominently writing that my amplifier is capable of rail-to-rail output voltage swing. What do they mean? Well, this is the positive supply rail here, VDD, and this is the negative supply rail here. So if you draw like this here and you draw like this here, what they're saying is that this output voltage can reach almost to VDD in the positive direction and almost to VSS in the negative direction. It can reach these are like two rails here. And the idea is that my output voltage can go almost as close to VDD here and VSS here without getting distorted, without getting clipped here. So output swing is as large as VDD in the positive direction, as low as VSS in the negative direction here. If that happens, we call an amplifier has a rail-to-rail voltage swing. Now, this is something that you have to take special things in mind in order to reach this one. Many times you may have a 5 volt power supply here, and all that you can reach is maybe 2.5 volt if you don't design properly here. So it's not automatic. You have to really design in such a way that it reaches all the way to VDD here and all the way to VSS here. So rail-to-rail output voltage swing is an important feature. Last one is, as I said, we'll not touch this particular one in this particular course, noise. It's a subject for a more advanced course, but I wanted to illustrate that this is something that is always present. If you look at this particular circuit, this was actually made in the lab. I have a 741 op amp, I have 100 ohms, and I have 10K here. And therefore, this circuit is capable of a gain of 100. And then I have another stage here, 100 ohms, 10K. There's also a gain of 100 here. And in between, is capacitively coupled here. Now, note that there are no sources in this particular circuit. No input. Input is grounded here, all these are ground. No source here at all. Right? So ideally, I would expect V01 and V02 to be 0. If I go and connect the oscilloscope right there, I would expect flat, 0, nothing there. What do I get? Here, look at this scale here. How much do you see? Scale is, I have to see carefully, 10 millivolt scale. This is a 10 millivolt scale here. Okay? Yeah, at this point. That's at here. Now things become really interesting if I go here. The scale is 2 volt. And see what you get? All this that you see here. Right? All this you get. Where is it coming from? No input here. No inputs anywhere. Right? And you get all this. It's not a bad connection. So it's not a bad connection. It's not a bad op amp. This is what you will get. So where is it coming from then? Huh? Initial conditions? No. No. These have been, when you connect to an oscilloscope and then you are seeing it over, after minutes, several minutes. So all those initial conditions, they die down. All transients die down after a 3 tau or so RC. So this is not initial condition. This is steady state. And this is what you see here. Now, where is it coming from? is coming from every resistor that you see here is a source of noise. This resistor is generating noise. This is generating noise. All of them are generating noise. By the way, the capacitor also, because it has a resistance in parallel and other things, has a noise. But more than that, if you go inside the op-amp, you have all these transistors. Inside 741 op-amp, you may have 25 transistors sitting there. And you have resistors. Every transistor is a source of noise. Every diode is a source of noise. They're generating noise. Okay? So all these elements are generating noise. And what happens is, so all of these generate noise here, and then you see a certain amount of noise here, 10 millivolt here. And so this circuit is generating noise, and you see here. Now what happens is this circuit will also generate a noise, roughly what? Of the same order, let's say 10 millivolt. But this noise gets amplified by this one. And therefore, the noise that you observe at the output is the noise generated in this part of the circuit getting amplified by a factor of 100 and appearing over here. Okay? So what it also illustrates is when you have a multi-stage amplifier, which, let's say amplifier 1, 2, and 3, which amplifier matters the most in terms of noise? The first one. Because you see, it has, this amplifier also generates 10 millivolt of noise. This also generates 10 millivolt of noise. But this one's 10 millivolt noise gets amplified by the second one. So it appears as 100 millivolt here. So the first amplifier is always the most important stage. Alright? So in the first stage that we build, we have to build it as a low noise stage here. We have to take special considerations in order to keep noise very, very low here. So the source of noise that you see here is all these resistors inside and transistors and diodes inside here. Another source of noise which is not explicitly shown here is that these op-amps are powered by power supply. Power supply that you think is 12 volt is not really 12 volt. That also has noise in it. And the noise from the power supply gets into your amplifier and then appears over here. So that could be another source here. The noise getting from the power supply also. Alright, so this is something to keep in mind. Now if I look at this one and I've built an amplifier like this, and if I ask what is the smallest voltage that my amplifier can amplify, what will you say? How small can it amplify? Can it amplify 1 millivolt? If I apply 1 millivolt here? If I apply at the input 1 millivolt, or let's say 0.1 millivolt. If I apply 0.1 millivolt, how much will be the signal at this point? 0.1 millivolt multiplied by 100, which is 10 millivolt. And 10 millivolt is what I see is the noise here. So the noise is comparable to the signal. So obviously my signal is getting drowned in noise. Normally I would expect, for an amplifier to work properly, I want at least a signal to noise ratio which is larger than 10 to appear as a nice clean signal here. So what I would want here is, let's say my signal should be larger than noise by a factor of 10, at least 10, let's say. Okay. Now for that, then I have to apply here 1 millivolt. If I apply 1 millivolt here, then I'll get 100 millivolt here, which is 10 times maybe larger than the noise. Okay. And then so what I can say is minimum signal that I can amplify is 1 millivolt. If I go below that, my signal gets drowned in the noise. Okay. So that sort of wraps up the important characteristics here. Okay. So from next lecture, we'll start amplifiers.